This is a video to illustrate the hand calculation of a one-way analysis of variance. The data that we will be using is artificial data from an alcohol treatment study. This data set was provided by Aaron and Aaron in the textbook Statistics for Psychology, published by Prentice Hall in 1994. This is from page 348 of that textbook. The first thing that we do when calculating a one-way analysis of variance is that we have to calculate the grand mean for all of the scores, and we have to calculate the mean for each of the groups. In this case, we have three groups: treatment A, treatment B, and treatment C. The null hypothesis of this one-way ANOVA is that there is no significant difference in the means for these three groups. In other words, they all come from a population with a common mean. In order to test that null hypothesis, we're going to be looking at the differences between the group means and the grand mean, and we're going to be looking at how much variability there is amongst those scores, and we're going to be looking at how much variability that we're finding within the groups. The analysis of variance test is essentially a look at whether or not the amount of population variance that is explained between the group means and the grand mean is significantly greater than the amount of population variance that is explained within the groups. So the first thing that we do here is we calculate the grand mean. The grand mean is essentially the average of all of the scores. So we add up all of the scores for group A, we add up all of the scores from group B, we add up all of the scores from group C, and we sum all of those scores. So in this case, the sum of all of those scores is 70. The sum of all those scores is 70. The sum of the scores for group 1 is 40. The sum of the scores from group 2 is 18. The sum of the scores from group C or 3 is 12. So we add 40 plus 18 plus 12, and that gives us a total sum of 70. We divide that 70 by the total number of observations, which is 10. So that gives us a grand mean of 7. So the average amongst all 10 of these scores is 7. We then look at what the mean is for each group. So in this case, the sum of the scores from treatment A was 40. We divide that 40 by the number of observations, which is 4, and that gives us a group mean of 10. The group mean for group B or treatment B is 6, and the group mean for treatment C is 4. Again, we determine those group means simply by summing the scores from the group, in this case 18, and dividing it by the number of scores. So at this point we have calculated the grand mean of 7 and the group mean of each one of these three: 10, 6, and 4. So the first thing that we are trying to do is we're trying to get a sense of what the overall variance of the scores are. So we're trying to get a picture of how far each of the scores varies from the grand mean. So to do that, we take each score and we subtract the mean, the grand mean. So the grand mean in this case is 7, so we have 8 minus 7, which gives us a deviation of 1. 13 minus 7 gives us a deviation of 6. 10 minus 7 gives us a deviation of 3. 9 minus 7 gives us a deviation of 2. We are going to end up squaring all of these deviations, just like we do when we are using the deviation score method for calculating variance and standard deviation in a sample, or when we were calculating t-test differences. For this course, we're using the deviation score method for all of this. So to do that, we calculate the deviation, and then we square these deviations. So 1 squared gives us 1, 6 squared gives us 36, 3 squared gives us 9, 2 squared gives us 4. So that gives us a sum of the squared deviations between individual scores and the grand mean of 50 for those subjects that are in treatment A. We do the same thing for the subjects that are in treatment B and treatment C. Again, first of all, we're focusing on the difference between the observed scores and the grand mean. So the grand mean was 7. So for this first subject in treatment B, we take their observed score of 7 minus the grand mean of 7, and that gives us a deviation of 0. 3 minus 7 gives us a deviation of -4. 8 minus 7 gives us a deviation of 1. Again, we're going to square all of those deviations, and we're going to sum them up. So this gives us the sums of the squared deviations between the observed scores and the grand mean for those subjects in treatment B. Over to treatment C, again, our grand mean is 7. So we take 6 minus 7 gives us -1. 4 minus 7 gives us -3. 2 minus 7 gives us -5. And once again, we square all of those deviations. So we end up with -1 squared is 1, -3 squared is 9, -5 squared is 25. These are the squared deviations between the observed score and the grand mean. We sum up these sums of squares. We add up these squared deviations to give us the sums of the squared deviations between the observed scores and the grand mean. And in this case, that is 35. So now we have the sums of the squared deviations for all groups for the subjects between the between the grand mean and their observed scores. So what we're going to be doing with that is we're going to just be summing up these sums of squared deviations. That is indicated down here. Okay, so we're going to take the 50 squared units between the group mean, between the individual scores and the grand mean here, plus this 17, plus this 35. So we have 50 plus 17 plus 35 gives us a total sums of squared deviations between the observed scores and the grand mean of 102. Essentially what we are trying to do with ANOVA, or anything that basically comes from the general linear models, we're trying to account for these 102 squared units. Okay? This tells us that not everybody across these three groups fell exactly at the grand mean. So we're trying to figure out why everybody is not falling at the grand mean. One reason is it's because the treatment means are significantly different, or at least one of the treatment means is significantly different from that grand mean, and then that's creating some of this. Another reason that everybody doesn't fall here, the other reason that we have a sums of squared deviations that is not 0 is because we have variability in how subjects are performing within groups. That is, their scores might vary a lot around each of the group means. So the next thing that we're going to do is we're going to see if there's a lot of variability around each of the group means. So for treatment A, we know that the group mean, that is the mean for subjects in treatment A, was 10. So we're going to subtract that group mean from each one of our observed scores for subjects in treatment A. So it's going to be 8 minus 10 gives us -2. 13 minus 10 gives us 3. 10 minus 10 gives us 0. 9 minus 10 gives us -1. These are deviation scores, so just as we always have done, we're going to end up squaring those deviation scores. So -2 squared gives us 4. 3 squared gives us 9. 0 squared is 0. -1 squared is 1. We sum up these squared deviations and we get 14 for group A, for treatment A. That's telling us that there are 14 squared deviation units between the observed scores and the group mean. We go over to treatment B and we do the exact same thing. The group mean in this case is 6. So for subject 1, we're going to subtract 6 from their score of 7. we're going to get a deviation of 1. For the second subject, we're going to subtract the mean of 6 from their score of 3, and we find out that that person was 3 units below the group mean. For the third subject, they scored an 8. The group mean was 6, so they scored 2 points above the group mean. We square all of these deviations again. So we have a 1, a 9, and a 4. We sum up these squared deviations, and we get a sums of squared deviations between the observed scores and the group mean for treatment B of 14. We do the same thing for treatment C, and we get an 8. And that is, again, based on subtracting 4, which is the group mean, from each one of these observed scores, calculating the deviation from that, and then squaring those deviation scores, and then summing those squared deviation scores. So just like we had done with the grand mean and the sums of squares total, we are now going to sum up all of these sums of squared deviations between the observed scores and the group mean. This is going to give us an indication of how much separation there was occurring within groups. So we're going to take this 14 here for group 1, right there, plus the 14 for group 2, plus the 8 for group C. We have A plus B plus C. So these are the sums of the squared deviation within groups. That means between the individual scores and the group mean. So there are 36 squared points of variability occurring between the observed scores and the group means. The last thing that we have to calculate is the differences between the group means and the grand mean. So what we now have is that we know what the group mean is and we know what the grand mean is. Okay, so the group mean in this case was 10 and the grand mean was 7. So we're going to subtract the grand mean from each one of these group mean scores, and that's going to give us a deviation. So our group mean was 10. Our grand mean was 7. So for each one of these subjects, their group mean score was 3 points above the grand mean. So we're going to end up accounting for each one of those 3 points. So this is 10 minus 7 for the first subject gives them 3. 10 minus 7 for the second subject gives us 3. 10 minus 7 for the third subject gives us 3. 10 minus 7 for the last subject gives us 3. We square those deviations again, and we have a sums of squared deviations between the group mean and the grand mean of 36 for treatment A. We do the same thing for treatment B. In this case, the group mean was 6. Again, the grand mean was 7. So 6 minus 7 gives us a deviation of -1 for each person. We square that deviation for each person, and we sum those squared deviations. So the subjects in treatment B are contributing 1 squared unit each between the group mean and the grand mean. We sum that up and we get a 3. We go over and we do the same thing for treatment C. The mean for the group in this case is 4. Our grand mean again is 7, so we take 4 minus 7 for each one of these subjects and it gives us a -3 as our deviation. We square that and we sum up the squared deviations between the group mean and the grand mean, and that sums of squared deviations in this case gives us 27. These are going to be the sums of the squared deviations between the group mean and the grand means. So we're going to add up the 36 plus the 3 plus the 27, and it's going to give us a total sums of squares between group means and the grand mean of 66. sometimes we confuse this SS between as an indication of sums of squares between groups. It's not really between groups. It's actually between the group mean and the grand mean, as you see by this deviation calculation here. It's looking at differences in the group means and the grand mean for each group. Okay, so this is the total amount of difference, squared units, between the group means and the grand mean. Each person is contributing a portion of this. Okay, so what we see is the subjects in treatment A and the subjects in treatment B were both contributing 3 deviation units that we would then square. The subjects in treatment B were much closer to the grand mean, so they are contributing less to this total sums of squares between the group means and the grand mean, because they were much closer, as you see from this sum of deviations of 3. Once we have the sums of squares total and the sums of squares within and the sums of squares between, we can see that the sums of squares total is essentially just the sum of the sums of squares within plus the sums of squares between. These two values here, this 36 and this 66, account for all of this. Okay, so 66 of these 102 squared units are due to differences between the group means and the grand mean, while 36 squared units are due to differences between the individual scores and the group means. The next thing that we do is we are going to go from these estimates of sums of squares to our estimates of population variance. Okay, so we now are creating this analysis of variance table where we're listing our sums of squares between, our sums of squares within, and our sums of squares total. So we are basically just transposing the information that we have here down to here. We are going to be making population variance estimates based on these scores. So we are going to be dividing by degrees of freedom rather than basic sample sizes in this case, because we are wanting to make inference to a population, so we use degrees of freedom. The number of degrees of freedom that occur between groups will always be based on the number of groups there are minus 1. So it's 3 minus 1, which gives us 2. You can see that math right up here. 3 number of groups minus 1 for the degrees of freedom gives us a total degrees of freedom for sums of squares between of 2. We divide 66 by 2, and we get a population variance estimate of 33 squared units between groups, actually between the group means and the grand mean. Within groups, we have our total sums of squares of 36. We figure out the degrees of freedom within group by basically taking the number of subjects that we have, which in this case is 10, and subtracting the number of groups that we have, which in this case is 3. So it's 10 minus 3, which gives us 7. Essentially what we are doing is we are losing 1 degree of freedom for each group. That's what's indicated up here. So we have 4 subjects in the first group, but we lose 1 degree of freedom. We have 3 subjects in the second group, but we lose 1 degree of freedom there. We have 3 subjects in the last group, but we lose 1 degree of freedom there. So it's going to be 3 plus 2 plus 2, which gives us the 7. Mathematically, this is the same as basically saying the number of subjects minus the number of groups. When we divide 36 by 7, we get a population variance estimate within groups, that is between the observed scores and the group mean for each group, of 5.14 squared units. Our F value is just the ratio of mean squares between groups divided by mean square within groups. So we divide 33 by 5.14 and we get our F calculated value of 6.42. This is a ratio, so this is telling us that we have 6.4 times more population variance being explained between the group means and the grand mean than we have being explained within groups. If this value of 6.42 is greater than our critical value for a situation where we have an alpha of 0.05, 2 degrees of freedom between, 7 degrees of freedom within, if this value is significantly greater than the critical value that we find under these circumstances in our F table, we are going to reject the null hypothesis that the three groups come from populations with equivalent means. What we see here is the F critical is 4.74. The F calculated is 6.42. That lets us know that our observed F value is greater than what would have occurred due to random sampling fluctuation alone when the null hypothesis is true, which is 4.74. Therefore, we reject the null hypothesis that the three group means are equivalent to the grand mean.